there's no real mathematical difference. Just a little more convenient, particularly for boundary value problems where you set up the system at time 0 and then you let it go off.
In this system, would we get a damping after?
So in this system, I haven't put in any damping. So this is the equation of motion. So actually, if you think about, that x is equal. So if we thought about the equation of motion for the response variable, there's, so x equal to x. So f, if now we think about f as ma, so x double dot is equal to k over m x. So if that's our equation of motion, then there's no damping.
So if we did the transform in this case, that's probably just keep on.
But just keep on going. We haven't done any damping. But, so that's, so this is the response function of the spring without damping. We could have a spring function with damping, and then we have a different response function without those damping response.
And for practical purpose, we're treating the impulse as a delta function.
So, practical purpose, yes. We will, so we can either do it as a delta function. For Laplace transforms, so for Fourier transforms, you often think about sines and cosines. For Laplace transforms, we think about exponentials. So we'll either use a delta function, or you could use the exponential limit of the delta function. So there are lots of functions whose in limiting form gives you a delta function. You can take a square wave and make it taller and taller and taller, an hour, keeping the area 1. So that's a delta function limit. You can also take an exponential, that the exponential decay is sharper and sharper and sharper, and it goes up higher and higher and higher. So that's a different function that gives you a delta function. When you're doing Laplace transforms, that can be a convenient delta function limit because Laplace transforms and exponentials get along very well. So get along very well means that it doesn't make the math any more difficult. And often, in a lot of real-world situations, the input is really better described as an exponential. So it's used a lot for drug perfusion experiments. So you inject somebody with a drug, the drug has to get into your body. What is the rate that drug increases in your blood given an initial dose that is not directly put into your blood and being put into muscle? Usually exponentials are a good model. So back to the spring example. So with the spring from physics 1 or 2, whatever, calculus-based physics, you know from the physics homeworks that you've done that all you need to solve this problem, like the spring problem, is the spring constant, and if you have some damping, you know what the damping constant is. And then if you know those, and the homework problem changes, how far you pull the spring at time 0, or how you're forcing the spring, you know you can get the solution. So the time-independent part of the system is that the system parameters, so the spring constant k, doesn't change with time. So that's what's time-independent. The spring can be moving with time, but the system parameters don't change with time. We can have systems where actually the system properties change with time. And the more complicated, we'll get to them, but we're going to start with time. So when we have, we'll actually work through, we might or might not work through, instead of just writing this down, showing how you actually just naturally get a formula like this, relating the input and the system response to the output. for now, what we'll say is that to solve a system like this, what you're used to doing is when you see a convolution, you know you can, if you Laplace transform both sides, then you change an integral equation into an algebraic equation. So you take the Laplace transform both sides, and you get this solution. So for notation, for my notation, the Laplace transform is indicated by a tilde. In other classes, I think sometimes use a capital letter, but I use the tilde. So we have x of t and x tilde of s are Laplace transform pairs. The system responds the effect at time t based on the force at the previous time t. Yeah. All right, so any questions at this point? So this is all in the notes on Monday. Although, I mean, this is sort of more, so this part is more sketching out what you had in previous courses. Then we're going to work through the yeast signaling example sort of all the way as a model for sort of the basic linear model for cells. So springs are the basic linear model for mechanical systems, the linear response, to really sort of get back to the spring. For cellular signaling, the analog, so what we always think about is a biomolecule with two different states, an active state and an inactive state, that switches between the two states, and that is the type of system that we'll study in depth. So it's sort of the basic system in biological signaling is the two states. So as opposed to a spring that changes continuously, here it's a molecule that changes between two states. So here's what we're going to do. We're going to focus on this step, that the way that signaling often happens. So here is that we have a TF for a transcription factor that is normally in the cytoplasm. And there are families of transcription factors that undergo reversible phosphorylation. So TF with a phosphate group attached, or some other post-translational modification that's reversible. And then they get the nucleus, they then go into the nucleus. So this transition is a chemical reaction. So whereas this transition into and out of the nucleus is the physical translocation. So usually chemical reactions are slower than physical processes. So this is the slow step. So it's the step that we'll focus on once the transcription factor is phosphorylated, it's radioactive. So adding the phosphate in these systems happens when the receptor is active. So the receptor itself, so many receptors have kinase activity. So kinase is just a protein that adds a phosphate moiety to another protein. And I guess I should say, you won't need to memorize details of biochemical models. You'll get a biochemical model. This is relating it to the experiments, and then we can look at the research papers and you'll understand what's going on. So a lot of receptors have kinase activity. The receptor is only active when the ligand is bound. So here's the ligand bound to the kinase. And then that makes it active. I guess I should show not bound here. When the ligand binds, it's active. And then it catalyzes the phosphorylation. And then there's a separate protein called a phosphatase that catalyzes the reverse reaction. So proteins with phosphate groups that attach will hydrolyze over time, so we'll lose the phosphate group. But actually, in cells, the phosphatases that speed up the back reaction to get the system back to a resting state. So what we are interested in is a model for the active transcription factor concentration as a function of time, as a function of the input ligand concentration. So our model is going to be chemical kinetics. So we're going to call the active transcription factor, we'll call it X of T. The inactive, we'll call it X0 of T. And we will have the X0 of T plus X of T is equal to the total concentration, which doesn't change. So in protein signaling, the concentration of signaling molecules usually doesn't change with time, or doesn't have to. Instead, it's their phosphorylation state or some other state that changes with time. So the number of transcription factors in the cell is not going to change in this model. Instead, what will change is how many of them are phosphorylated versus not phosphorylated. So chemical kinetics is then we are focused on dt of X of T is equal to K forward times term T times X0 T. So I'll write down both terms and then we'll go back to them. Times K backward think about as a biomolecular rate constant between the inactive form of the transcription factor, so the unphosphorylated state, times the concentration of the active receptor times a rate constant. And the active receptor is just the receptor with ligand bound. So we could, so essentially that is proportional to the ligand concentration at the time. And then the unphosphorylated transcription factor, in the linear response region, it's sort of, linear response is the region of very small input. So if the input is very small, then the output is very small. And what that means here is that we are thinking about the case where x of t is much smaller than x total. So most of the transcription factor stays unphosphorylated, and x0t is about equal to x total at all times. So this will be our linear approximation, that for the most part, only a small fraction of the available transcription factor is phosphorylated. So we're doing that in order that we can treat the system linearly. So when we're all done, we have to go back and check to see that really the system is in the linear regime. But we're going to make the simplification at the start. The way that you check an approximation like that, one way is to check to see that you don't have things going to infinity again. So we want to check, we'll check that now, but here this is x total. So now what we have is a physical constant, forward rate constant. We have a concentration of transcription factor that is essentially constant in the cell, and then something that we control. So we have an oscilloscope that is controlling pumps that are pumping in fluid. So we know the ligand concentration at least to an overall proportionality constant. So within an overall proportionality constant, this is something that we control overall. And because these are all constants times something that we control, we'll simplify our notation and just call it theta of t. So this is our input. So it's input that we control. Yes. So this term? So what we're doing is we're keeping all terms to lowest order. So this term, the lowest order term, is x total. So it's huge, but when we multiply by k out, it's no longer huge. When we multiply by k out, it's going to be in the same order as x. So that's the way we're going. So here, so it's more that we're keeping the leading order for each term. So this term and this term will be about the same size. So the reason is that this forward rate constant ends up being small. So it ends up being small enough that even though we're multiplying by x0, it gets it sort of on the same scale as this. Or at least that's the approximation. In reality, what we really need to do is then look at the system and say, is this approximation right, that this term and this term are on the same scale? And the answer is it really depends on the system. You have to look at the system parameters for the systems that we're looking at. It actually ends up being good. There's another handout over there somewhere. Yes?
So I'm a little confused as to why we're putting beta of c as the input. I thought earlier we said beta of c would be our output.
That was I haven't had enough coffee. So in that one I said beta t is the output, is the output, but we're going to use it really in the class use it as the input. I just was not used to that SB3. Sorry. I should have said something because I was writing down, oh wait a minute, I just should have. So thanks for that. Yes, so consistently beta 2 will be the input. Going beta. So now, this backward rate constant is it's called a constant because it's a constant. I mean, actually, it depends on temperature, it depends on probably ion concentration, whatever. But we'll consider it a constant. And phosphatase, we'll consider the concentration of phosphatase essentially a constant. So these two constants, when we multiply them together, they're still a constant, and we will call that alpha. So that's a grid alpha not proportional to. And so this is our decay rate. So decay rate, as in, we're thinking about x as the active form. And so when it decays back to the inactive form, that's decay, and alpha is our decay rate. So we put this together, and we get ddt of x of t is equal to beta of t minus alpha x of t. And so this is going to be, so this is the equivalent of our F is equal to kx for springs. So this is a two-state biological system that is activated and then relaxes. The input for activation is beta of t, and the decay rate is alpha for a system that's in the linear regime. So here, this is a yeast cell. We're changing the concentration of the media just a little bit. We're not killing the cell. We're changing it just a little bit where the response is linear. And if you're doing this experimentally, an easy way to check the response is linear is then you double the size of the input. So you double the amplitude of the input, and you check to see that you double the amplitude of the output. So it's just a simple, pragmatic way of checking that you're in a linear regime is that if you hit it twice as hard, it should respond twice as hard. If it doesn't respond twice as hard, then you're not in a linear regime. So it doesn't really work with hitting siblings. Like when you hit the sibling, no matter how hard you hit the sibling really screams. So I haven't detected a lower amount of the linear response to hitting siblings.
Will we consider systems where the alpha is dependent on?
So here x is the output. Yes, but what I'm saying is, so here's what I'm saying. That say you change the magnitude of the input by a factor. All right? Then in a linear system, you should change the magnitude of the output by a factor.
I understand the point of the movement. I'm just wondering if it's a bit more complicated later, of course, where you have alpha dependent on beta.
Yes. So complicated in a way, but also, so now let's imagine what would happen if you really pushed on the system hard. So how do we deviate from linearity if we push on the system hard? The way that we deviate is that instead of always being close to nothing being activated and then sometimes be a little activated, so here we have, say, fraction active. Actually, that's not what we get instead is that we get all the molecules in the active state. So instead of thinking about a system where most of the molecules are in the inactive state and then we get some in the active state, instead we think about a system where when we hit it, there's sort of a collective response that everything goes to the active state. So in biological systems, that's called cooperativity. Hill functions, yes, exactly. Well, like hill functions and titration types. So yes, we'll work out how cooperativity gets hill functions, but it's a hill function type response where you're usually either in the inactive state or the active state, and instead of having sort of a continuous response, you get a binary response. That at the system level, all the transcription factors will either be So wouldn't exactly be transcription factors, but like you're activating a gene. So this pathway turns on genes that turns on defense against high concentrations. So you'll have a system where either the genes are transcribed or not. So you're being more of a two-state system as opposed to a continuous system. So it's an on-off switch. On-off switches are non-linear versus a continuous response system. So now to solve this system, so if this were an algebraic system, you know, what you would do is you would get all the x's onto one side. So we move the x onto one side. So here you're thinking about the derivative as an operator. So the time derivative operates on functions of time. And that alpha is just scalar, and that should be a plus sign. And then to solve it, you would just take the inverse. So x of t is equal to dt plus alpha inverse beta of t. So the problem is that you don't know how to take the inverse of a time derivative operator plus a scale. So why don't we just because we could do that, and then we have x of t as a function of an integral of x of t. So the answer is yeah, we could do it. That's sort of the integral equation way of doing it. The way that we actually do it is that we think about special sets of functions where the idea is so we think about special functions where ddt of some function phi lambda of t is equal to lambda by lambda of t. So we think about functions that are eigenfunctions of the time derivative operator. Yes?
Can you use integrating factors?
So, I mean, really what we're going to use is just transforms. So how could this be an easy problem? This could be an easy problem if the time derivative of this function gives us the function back. And the types of functions, those are functions where when you take the time derivative, you get a constant times the function. So we think about it similarly to how we do this with matrix algebra, where we think about eigenfunctions and eigenvalues of matrices. So what we're going to do next time is we're going to see that if we write x of t as the sum over functions of x, x of s e to the minus st, that we're able to solve it easily and we'll get solutions.
So the Laplace transform to x end up being the eigenfunction.
They're the eigenfunctions of the time derivative operator. So really, so what's going on is when you have a matrix equation, you know what simplifies a matrix equation is is to express your answer in terms of the eigenfunctions of the matrix. So here we have an operator equation where the operator is the time derivative. If we express our answer in terms of eigenfunctions of the time derivative, then we have an easy solution. And getting the eigenfunctions and the coefficients of the eigenfunctions is just taking the apart. So that is where we'll end for today.